your creation annihilation operators move you between the different subspaces of different numbers of particles, right? If you act with any of the creation operators, you move from n particles to n plus 1 particles. So if you're working in a subspace with a fixed number of particles, then you want to make sure your operators have equal numbers of creation and annihilation operators, right? Because you want to make sure that in the end you pop in as many particles as you pop out. So we also had an interesting talk about during recitation about how this connects to what we did before in terms of identical particles. And remember, we did do 2 spin 1/2s, right? And we talked about how you have both the spin triplet and the spin singlet. Remember, the triplet was the set of states like this, with the symmetric combination, and the spin singlet was the anti-symmetric combination, up, down. And it's kind of interesting, right? If you think about how this would work in second quantization, it's a little bit confusing because you would think that naively, right, these states wouldn't be allowed because you can't put 2 fermions in the same state, so they can't both be spin down. But that's not how it works, right? Because apart from the spin degree of freedom, these spin 1/2s will, their electrons say, they'll have some spatial portion of their state. They might be located at some coordinates R1 and R2. And so it's kind of fun to think about, right? We know that for the spin triplet, we know that we have to have an anti-symmetric total wave function. So we know that the total wave function for the 2 particles in this case is a product of the spin triplet piece, and then it has to be an anti-symmetric combination of the spatial wave function. So if these are some energy levels, then you have to. And what's interesting about it is if R1 is equal to R2, if you try to put the electrons in the same place, then this whole thing vanishes, right? So indeed, that's another manifestation of the fact that you can't put 2 fermions in the same state. So although it seems naively that these spin triplet states have the fermions in the same state, they're not, because you have to also take into account the spatial degrees of freedom. And that's what we're going to talk about today, is how you introduce spatial degrees of freedom, like the locations of the particles. How does that come in to the picture? So far, we've been dealing with creation annihilation operators like this, which put the particles in some state I, right? And we haven't really specified what I is, but typically it'll be like an energy level. But there's nothing preventing us from, this should fully specify the quantum state of the particle. This is the full sort of state of our particle. And there's nothing preventing us from including the position of the particle as part of the specification. We can assume that we're looking at generating particles at fixed locations, say, and we know that those states are not normalizable, and so on and so forth. But that's okay. We can still kind of deal with it. or you could normalize it by, putting the particles in a box and going from there. And that's what we'll do today. But before we do that, I wanted to give an example of applying Wick's theorem. So that's what we did last time. We sort of derived Wick's theorem. It's a very nice theorem. It's used all the time in field theory and statistical mechanics. But in the context of the second quantization stuff, the formula, the theorem is just that if you have a product of creation and annihilation operators, a bunch of them, then this product is equal to, and these guys can be either, creation or annihilation operators, either one. Then this product is equal to the normal ordered set of operators, where you put all of the annihilation operators on the right and all the creation operators on the left. And then what you do is you go term by term here in this expansion. What you do is for each term, you basically sum over all the contractions of operators. So the first term is a single contraction where you contract two of these operators, any two. And so you have a sum over all the pairs of operators in your product. And you don't want to double count, so that's why you sum over all j is less than k. So you just want, all the pairs of all the pairs of operators that you can choose out of here. So you pick any two, and this is just indicates that you don't want to overcount. And there's a -1 to the p, and that has to do with the number of operator exchanges it takes to get the two operators you're contracting next to each other. And this is only for fermions, right? Because of the anti-commutation property. Then you have a vacuum expectation value of those two operators that you picked out. That's what a contraction means. You just take the vacuum expectation value. And then this is all multiplied by the normal ordering of the rest of the operators. So A1 to AN without A, J, and K. So basically, the normal ordering of the rest of the operators with those two, AJ and AK, pulled out. And then you go on. Then you do two contractions. So you have pairs of sum over two different pairs, right? We can pick out a JK and we can pick out an LM, say. And then again, it's the total number of, you count up the number of operator permutations, just exchanging two neighboring ones, however many it takes to bring the two pairs next to each other. If it's odd, then you pick up a minus sign. If it's even, then you don't. So for fermions, so you have that. And then you just have the vacuum expectation values of those two things. So you have two contractions, right? And then this is all multiplied by the normal ordering of, again, A1 through AN. And this time it's without AJK and without ALM. And so on. You keep going until you've contracted all of them. And you're left with either one operator or, none. So that's Wick's theorem, and I just wanted to do an example. Let's do an example for fermions, because that's kind of the tricky one. So let's have fermionic operators, and we have AI dagger, AJ, AK, AL dagger. So let's look at this. All right, so the first term is just a normal ordering. So we keep the relative order of these, we just move the annihilation guys over to the right-hand side. So that this would be AI dagger, AL dagger, AJ, AK. Next term would be all of the pairwise contractions. So a single contraction. And there's a bunch of terms like that. There must be, so let's see how many. You can do these guys, right? You could do these guys get contracted. You can put these guys contracted, these ones, and the outermost ones. So that's a total of 1, 2, 3, 4, 5 terms. There should be one more. Let's see, which one am I missing? Yeah, the first and the third one. Right, you can contract these two guys. That's another. So there's 6. So you can just write them out. So the first term is we can contract AI and AJ. They're already together, so we don't need a plus sign. Right, so I got this. And then the rest of it is going to be the normal ordering of AK, AL dagger, right? And that'll just flip the AL and AK. Now we can do a contraction of AI with AK, for instance. And look at this. AI and AK are one operator apart. So you have to exchange these two operators in order to get AI next to AK. So this has to come in with a minus sign. And then the rest of it is just the normal ordering of AJ, AL dagger. And you can go on. Then there's contraction between AI dagger and AL dagger, right? And that requires 2 flips, so that's okay. And then you have the normal ordering of N, AJ, AK, and then you don't have to do anything with that. Then you have a contraction between AJ and AK. Again, they're already together, so you don't have to do anything there. That. Then you have AJ and AL dagger that you contract. These are one operator apart, so this requires us to flip these two guys. So you pick up a minus sign. And then you get the normal ordering of NI dagger, AK, right? So, okay, we have 1, 2, 3, 4, 5 terms. There's one more. That's the contraction between AK and AL dagger. And these are already together, so there's no minus signs, the normal ordering of NI dagger, AJ. And now you, of course, have all the fully contracted ones. There's 4 operators here. So the next term is the one where everything gets contracted, and there's 3 terms like that. And the way you can draw those terms is just pair off all the operators, and you can again use these lines to kind of indicate that. So like one contraction is these two guys, another contraction is these two, and then the third one is where they pair off like that. So you have all those. The first one doesn't require any minus signs because all the operators are next to each other. And then you have the ones where the inner and outer ones are connected. That also doesn't require a minus sign because that requires 2 exchanges of the operators to bring them together. But then the other ones do require, the other one does require a minus sign because you have to flip the 2 inner ones in order to get the operators next to each other. And that's the AI dagger, AK, AJ, AL dagger contraction. And of course, a lot of these will vanish. You know that whenever, again, these are vacuum expectation values. So whenever an annihilation operator hits the vacuum, then you just get 0. So this guy, you know, is 0. A I dagger, a J, 0. So this is 0. This guy's 0. This guy's 0 because you pop in 2 particles and then you sandwich them in. What else is 0? These guys are 0. This guy may or may not be 0 depending on whether L is equal to J. So you might worry about that. This is 0. This is 0. And this is 0. So you see there's very few things left, right? You get that this is a I dagger, a L dagger, a J, a K. What do we even have left? We have minus this guy. Well, this is going to be 1 only if J is equal to L, right? So we got this. And then the normal ordering of these guys is just a I dagger, a K. So it takes care of that term. Then we have this guy, which is going to be 0 unless K is equal to L. And otherwise, we got the normal ordering of this one, but it's already normal ordered. So we're good there. And I think that's it. Yeah. So there you go. That's how you use this formalism. Any questions about that? Okay. So I'm going to clear this then. So that's the setup. And now what we're going to do is think about what happens for the position basis. So remember that, instead of I, the state I, we can move to just coordinates. And we can think about a particle at some position R, and maybe it'll have some spin. So this is the position of the particle. And this is maybe the spin. Spin 1/2 could be spin up or down or something. And we know these things are, of course, orthonormal. So they satisfy the orthonormality condition, except the only difference is with the regular state is that they're normalized, they're orthogonal with respect to this direct delta function for the coordinates instead of the Kronecker delta that you would normally have. So again, this is just because we have these R states represent continuous spectrum, right? So we need an infinite dimensional kind of ideas to do this. So if you go back to the first semester, we talked about what position space representation and so on. We saw that you could define eigenstates of position. It's just that they won't be technically part of your Hilbert space. They'll actually be outside of it because you can't normalize the states, but you can still treat them as if they're eigenkets of the position operator. And the only difference is, well, I mean, among other things, just that their orthonormality condition comes in with a direct delta like that. But otherwise, it's fine. So there's nothing preventing us from taking our creation annihilation operators and replacing them with creation annihilation operators for particles at specific locations. And we introduce capital psi here to do that. This one annihilates a particle at location R and spin state sigma. And this guy creates a particle in spin state sigma at position R. And we actually also know how these are related to the momentum basis, right? We know that there's a simple connection between the there's a unitary transformation, right, that takes us between position space and momentum space representation, and that unitary transformation is just the Fourier transform, as we know. So for that same reason, the field operators in position and momentum space are related to each other, and we could make the we could put the particle in a box so that that relationship becomes a Fourier series with discrete values of k corresponding to box normalization, just putting the particle in a fixed box. And in that case, the creation, the annihilation creation operators corresponding to particles with fixed position or momentum are just related by, our friend the Fourier series, which is e to the I k dot r a k sigma, right? So this is an operator, and well, let's put daggers on them, I guess. Guess we put daggers. We have to. So this makes a particle, right? Makes a particle with spin sigma at location r, and this makes a particle, all right, with momentum h bar k, and spin sigma, spin state sigma. So it's the usual relationship. Remember I said that all sets of states you use, whether the positions or the momenta, the creation annihilation operators are related to each other via unitary transformations. In the case of position and momenta, it's just the Fourier series. And so everything kind of follows through exactly the same way for these real space guys, except their commutation relations are just going to be a little bit different because they correspond to states that are not properly normalized. These guys are okay because if you put the particle in a box, then that's fine. But generally speaking, these operators, they would have this kind of normalization, right? With the direct delta function, because R can be continuous. If you put the particles in the box, then the momenta are going to be discretized, and then you have proper kind of orthonormality condition, as you would expect. But the positions, no. So what that means is, of course, that that you get the same commutation relations and stuff, but the normalizations are different because the coordinate is continuous. But for bosons, you again have that the creation and annihilation operators commute. So if you take two of them, two different states, or you take two creation operators, these guys commute, so these are 0. And the only thing that's different is that if you have the mixed ones, right, then they'll commute unless the spin states are equal and the coordinates are equal, and this comes in with this direct delta function, right? So it's the same thing as before. Remember, before we had commutator AI. Ooh, there's a dagger here, of course. AJ dagger is delta IJ. Well, it's the same thing, except now you have a continuous variable labeling your states, and that's okay as long as you treat it properly as a pseudo eigenvector with the associated caveats with it. Same thing for fermions. So you have creation annihilation operators for fermions, and those just satisfy anti-commutation relations. So same thing. Looks just as before, except, the continuous part of the spectrum, the position coordinate, it comes in with this delta function for the mixed commutation relation. And of course, when you're constructing operators and stuff like that, instead of summing over all the states I and j, you integrate over the coordinate. So for instance, so now you have operators, right? What are the operators? Well, you can have the total number of particles. Same as before, what you do is you sum over all the states. In this case, you sum over all the spin states and you integrate over all the coordinates. That's the equivalent of summing over I, right? And what do? Well, you do the creation operator, right? And the annihilation operator. This is the sort of moral equivalent of A dagger AI, the number operator for state I. What you see now, this thing, this product of these guys, right? This looks like a density operator, right? So this is really a kind of particle density operator, because once we integrate over it, we get the total number of particles. So this is a particle density operator. Sometimes it's called that, rho sigma, for a particular spin state. Of course, this is the density of particles that observable for a particular spin state. It looks an awful lot like a probability density, right? Like wave function squared, but it's not. It's very important to recognize that these psi's are, in fact, creation and annihilation operators. They're written in terms of size, size for historical reasons, but they are operators, and they're not wave functions. So it's just, these are, they're the same as AI dagger AI, but for position space. Something important to keep in mind, and this is why this is called second quantization, right? Is because first quantization is sort of the introduction of wave functions for a single particle, and then in second quantization, what happens is your quote unquote wave functions get promoted to operators now, the creation and annihilation operators for creating particles in particular locations. That's kind of a little hand wavy way of thinking about why it's called second quantization, but it's mostly a historical accident. It's probably not a very good name, because you're not really second quantizing anything. It's just a name for this procedure. It's not a very meaningful name, but that's one way to think about why it's called that, I guess. Okay, so that's the number of particles, and of course you can have any one body operator that you want in a similar fashion as we had for the states AI and AJ and so on. Any one body operator you can write as a sum over two sets of states, right? So you have to sum over sigma, sigma prime, and then two integrals, dr and dr prime, of what? Of the creation operator for one of them, sigma r prime. Then you have the single particle matrix elements. These are the position space matrix elements, right? Between two locations and possibly two different spin states. And then this is the number, and then you have the annihilation operator. Moral equivalent to, right, sum over ij, I dagger I h1 j aj, right? This is the equivalent to that, except you have a continuous variable now, the coordinates, so you have to integrate over that instead of sum, and but otherwise it's exactly the same. So that's the general form of the one-body operator. And you can have two-body operators that describe interactions between pairs of particles. Two-body or two-particle operator. What does that look like? Well, now you have, it's convenient to define it with a factor of a half, something I didn't mention before. I didn't, when I talked about the pair distribution function, of course, and this is on the quiz, so as a hint, if you have, right, if you have particles in state I and state J, right, and you have like some in here and some in here, the number of ways of picking out pairs of particles is going to be, you pick out a particle in state I, so there's Ni, or state J, and there's Nj of those. Then you multiply by the number of particles in state I, it's Ni of those. But of course, it doesn't matter which order you pick them in, so the actual number is divided by 2. That's the number of pairwise ways of picking out pairs of particles from those two states. So, and of course, if it's in the same state, then it's Ni minus 1 over 2. So you often define you often put in this half here for that reason. I didn't really mention that before, but should make sense. You just don't want to double count pairwise interactions. So what do we have here? Again, the two-body operator is you have a sum over 4 states, right? So it's a little bit awkward to write down, but let's write it down. Sort of, we're in no rush in particular, so. So you have this guy, right? And then you create particles in states, first state and the second state. Then you annihilate particles in the third state. Let's see. Yeah. Sorry, 2 primes here, right? 2 primes and then 3 primes. And then your matrix elements are going to be between R sigma and R prime sigma prime. We have some pairwise interaction. And remember that the order of the third and fourth states are flipped in the matrix element. That's important. So it's just as the same as what we had before, except you have integrals over the coordinates.
Would that be V2? Or
we could call it V2. Yeah. Oh yeah. Sorry. Yeah. V2. 2 particles. Sure. Yeah. So what does this do? Again, it pops out 2 particles, right? A pair of particles in 2 different states, and it pops in 2 other particles in 2 other states. And these matrix elements tell you the transitions between a pair of particle in this state and a pair of particle in some other state. So that's why it's kind of written in terms of this kind of Feynman diagram, right? You start out with a pair of particles in these 2 states, and then you end up with a pair of particles in some other states. And this is sort of, well, it's basically, well, what will happen is, right, is that you can't treat, so what actually happens? How do you use this kind of thing, right? So what would you do? Well, you would have some, you would typically have some piece of the Hamiltonian for your system that's not interacting. It's just a bunch of single particle operators that describe, say, the kinetic energy and the potential energy of your particles, right? And so what that would look like is in position space, you would have, and I could call this H naught. I would have a sum over, sigma prime and an integral for R, or maybe just over sigma. I guess you don't need the prime. You would have sigma. You'd have psi. You'd have it'd be diagonal in a position space, say, and the kinetic energy looks like this, and then there'd be some potential, right, describing the potential that each particle experiences, right? And you would have this as your kind of unperturbed Hamiltonian, say. And then what you would do is you would include this kind of term, this pairwise interaction term, as a perturbation. And then you could do perturbation theory order by order in say the two body interaction term. And that's where the Feynman diagram technique would become useful, because you could, at different orders of the perturbation theory, right, you would have different numbers of these interaction vertices that you'd have to use to construct your perturbation theory expansion. So that's that. And you would do this in a sort of advanced solid state condensed matter course. This would be kind of the starting point. You'd go on from there and sort of do that stuff, but it's outside the scope of this class. So what I want to talk about now instead is I want to talk about the multi-particle states themselves. I want to, so these are the operators. Maybe we'll do a little bit more of this next time when we talk about QED or something for the last class. But for now, let's think about what about the actual what about the multi-particle wave functions? How do those come in? Remember what those were, right? We had single particle wave functions, right? And say these guys, and we would make symmetric and anti-symmetric combinations of them to get like fermionic and bosonic states, right, of identical particles. So we take symmetric combinations for if we want symmetrized part of the spatial wave function, ignoring spin, say. And for fermions, we take anti-symmetric combinations. So it's nice to see how the second quantization stuff ties into that. That's what we're going to see now. So again, yes. So the symmetric combination would be like 1 over square root of 2. You get psi A R1, right? Psi B R2, plus the particles reversed. Like that, right? That would be the symmetric combination. It's symmetric under particle exchange. The anti-symmetric combination is same thing, but with a minus sign. That's what we started with this whole section, right? Is looking at this kind of stuff. And we had the Slater determinant if we had more particles. So where does the Slater determinant in all this second quantization business? Well, how to see it is you first might want to consider what does a multi-particle state look like in the position representation? What if we wanted n particles and each one is going to have some spin and coordinate, right? Like this. Say there's n of them. The way you would construct this is by applying the creation operator to the vacuum. You'd pop these particles into existence at those locations and for those spin states. Now, it turns out that there's a normalization. The normalization ensures that when you take the expectation value between, what do we need, right? We need the expectation value of the state, right? Well, we need it to be normalized, right? We need it to give us a bunch of delta functions, right? If this is a tensor product, right, of particle and location R1, R2, and so on. So when we, when you do like R1 prime, right, sigma 1 prime, and so on, you do this normalization, R1, sigma 1, and so on. You better get a bunch of Kronecker deltas for the spin part, and you better get a bunch of Dirac deltas for the coordinates, right? So it has to be normalized like that, we know. So in order to have that normalization, you need a 1 over square root of n factorial. And I'll argue for that in a moment. And then what you do is you just pop particles in all those locations, right? Acting on the vacuum. You take the vacuum with no particles in it, you pop in a particle at location R1 with spin state sigma 1, you pop one in at location R2 and state sigma 2, and so on. Sigma n, dagger, Rn. And of course, what if I try to compute this inner product, right? If I take this and I take the inner product of it, well, as promised, everything reduces to vacuum expectation values. This thing, right, in terms of this, is going to be 1 over n factorial. Then it's going to be a vacuum expectation value of annihilation operators, sigma 1, R1, and we'd have to yeah, so these are primed now. So when we take the bra, right, we have to undo these daggers so they become annihilation operators. And we have prime coordinates here, so these become annihilation operators at the prime coordinates. A bunch of them. And then we have a bunch of the creation operators, right? For the unprimed coordinates, all the way up to sigma 1, R1. But look at this. It's just a vacuum expectation value. And I told you by Wick's theorem, the only term that survives this is all of the pairwise contractions. And those pairwise contractions will just give you delta functions. And in fact, the number of pairwise contractions will actually be, there'll be n factorial of them. And so you can kind of convince yourself that that's the case. Because you have to pair off all of the particles. So you end up getting that you're summing over all permutations of the n particles. And so what you end up getting is so I didn't, so this is almost right. So this it's subtle. So this is true for distinguishable particles, right? This is what we would get. But if they're indistinguishable, then we know that in principle, it's going to be either symmetrized or anti-symmetrized states. So what you should actually get is the result of whatever this computation gives you, which ends up being 1 over n factorial, sum over all the permutations of particles, meaning all relabelings from 1 to n. And you get minus 1 to the p. That gives you the right minus signs that would come in from like the Slater determinant. And then it's all the delta functions between the different prime and unprimed coordinates. So I'm going to do an example of this for like n equals 2 to see how it works, so that this is a little bit less abstract. But you should, so this isn't quite right. So this should be equal to the sum over all the permutations of this stuff, where you relabel all the particles, right? Because they're identical. So what we're seeing here, right, is that this state, right, for having n identical particles in different locations, it has the right kind of features, because the creation annihilation operators incorporate within them, due to their commutation or anti-commutation relations, the right symmetrization or anti-symmetrization. So when you calculate the inner product between these two states, you'll get all the right either symmetric or anti-symmetric combinations. Why? Essentially from Wick's theorem, because if we take this multiparticle state as being defined as this, right, then we get the right thing for the for the inner product between two different multiparticle states of identical particles. It's going to be either a symmetric or anti-symmetric. So what is the wave function? The wave function then is just a position representation of the state. The wave function psi of, you know, R1 sigma 1 R2 sigma 2 is just the inner product between this position basis and whatever your actual state is, your multiparticle state of n particles. And this guy could be generated by, you know, like if you're at a particular, if the particles are in particular energy levels, right? This would be sum over all the different occupation numbers, some coefficients, right? You'd have the normalization. This is what we had before when we were talking about just regular creation annihilation operators. And these guys could be, you know, a bunch of the creation operators for all the different, for all the different states that we have. So I'm going to do an example to make it more concrete. Show you how it works. And this is acting on the vacuum. So this creates particles in particular, you know, it creates a particular multi-particle state with different linear combinations, say, of different occupation numbers, something like that. Or you could just, you know, this could be actually an eigenstate of, you know, it could be just a single occupation number state where, like, you just specify the number of particles in state 1 or something, right? And, you know, and so on. Could be just one of those. So it's the inner product. So let's calculate this inner product for, and of course the key is we're in this n particle, we're for a fixed total number of particles. So you also need that the sum of all the occupation numbers is equal to the total number of particles. So that's something else that you need for this. But so let's do an example. Let's do just n equals 2 particles. So your wave function then should be R1, R2. And remember, this should be, what should it be? It should be either a symmetric or anti-symmetric combination, depending on whether or not you have bosons or fermions, right? So let's do it for bosons, say, without spin. So we don't have to worry about spin. So what would this be? It would be the sum over ij of Cij divided by square root of an I and j. And then we have the vacuum expectation value of sigma R2, psi R2, psi R1, acting on AI dagger, AJ dagger, acting on the vacuum. So this is, what is this? It's just, this is just, again, it's the inner product between R1, R2, and a two-particle state, an arbitrary two-particle state generated by these creation operators. That's what this is. But we can actually calculate it out, right? So let's calculate it out. There's going to be two cases, one in which I is equal to J and one in which I is not equal to J. And there's just two particles, so there's only two possibilities. Either they're both in state I, or one is in state I and the other one is in state J. So we get that this whole thing, sum over I not equal to J, Cij, and we get that this is, and of course this is just one, there's one particle in state I and one in state J. And then you have 0, psi R2, psi R1, AI dagger, AJ dagger. And then you also have plus I is equal to J, just a single sum. Then you have two particles in state I, so this becomes Ci over square root of 2. And this is the vacuum expectation value of psi R2, psi R1, and this is AI dagger, squared. Let's just say AI dagger squared. This is for bosons, so they can be in the same, state I there. So, all right. And now, if you look at these things, what are these things? These are just the product of the wave functions, because what happens here is you make a particle in state J and the particle in state I, and then you sandwich that with this guy, which is just the coordinate basis R1, R2. So what you get is these vacuum expectation values, they're just going to be sums of the wave functions. And let's see, what else should I say about that? No, I guess that's it. And so this will include a sum over I and J, right? And so it'll include terms where a particle, where you have, it'll include things like psi sub I R1, psi, and these are the wave functions now, R2, and then it'll include the other combination where you have psi R2 and psi J R1. And this guy will also have the possibility of having just a product of wave functions where both of the particles are in state I. Like that. Sum over I, and this is over all I not equal to J. So this will include all the symmetric combinations of psi R1, psi R2. So let's see. Yeah, and the way you, and I'm skipping a little bit. So the way you would do this is, of course, it's the same way as before, where to calculate these expectation values, what you would do is these are annihilation operators, right? And these are creation operators. So you'd want to move these annihilation operators past these guys and hit the vacuum, at which point things will vanish. And that's what gives you this symmetric combination is once you do that, you'll just get the wave functions. Why? Because it's basically like it's just another application of Wick's theorem, because what happens is the commutation, you actually have a commutation relation, right, between the annihilation operators for the coordinate and the creation operators here for these guys. And these guys are just the wave functions like this. So you can use this commutation relation, and similarly anti-commutation relation for fermions. You can use this to go from these expectation values to just the products of wave functions here. And so why do we have this commutation relation? Well, because remember that the relationship between the annihilation operator, right, and the annihilation operator for the state, these are just different representations. They're different bases of the single particle states. We can either use positions or we can use, say, the energy representation. And so we know that the relationship between the annihilation operators must be some unitary transformation, and must look like that, right? It's the same as, it's the moral equivalent, right, of the b sub i's is equal to sum over, or maybe b sub j is rather sum over I of some coefficients, the inner products between states Li and Kj, switching basis in the one particle space, like that. It's the same thing, except just specialized to a transformation between like an energy basis and the position space basis, the coordinate basis. And these guys are just the wave functions. So this is sum over I for, say, the energy basis of the wave functions, single particle wave functions. So you have this relationship. This is just because these are just the inner product, right, between R, the position space basis, and whatever your states are, right, the energy levels, say, for your single particle. So it's just a transformation like that. And so so what was I going to say here? So you can just, well, let's figure it out, right? We could just calculate this, this guy, right? Psi r AI dagger minus AI dagger psi r, that's the commutation relation, is equal to sum over, I have to introduce another variable j, say these are the wave functions j, r, and then we have a j now, AI dagger, and then for the other term we have minus sum over j, wave function psi of j, r, and we have, this time we have AI dagger aj, right? So we can combine these two things, and what we get is sum over j, psi j, r, and then we have the, and again, these are the wave functions. And then we have a commutation relation between aj and AI dagger. But we know that this thing is just equal to delta ij. So the sum gets killed off and we're just left with a single wave function in the ith state, like that. So that proves it. That proves this commutation relation. And so it's basically just Wick's theorem again. We have an expectation value, right, of some annihilation operators and some creation operators. And you can rewrite these annihilation operators as linear combinations of, you can just put it all in one basis if you want. And once you do that and you use the commutation relations or Wick's theorem, you'll get all the right symmetric or anti-symmetric combinations for the multi-particle wave function, right? So that's kind of how it works. So hopefully you sort of see that, that by using these definitions that are, that this basis is equal to this, right? A bunch of creation operators acting on the vacuum, then we can construct any kind of multi-particle wave function by taking any multi-particle state, which we generate by using creation annihilation operators for, you know, our states of interest, could be energy levels, whatever, what have you, and sandwiching them with the position space basis. It's the same as we did for one particle where we took our state psi and sandwiched it with, you know, a coordinate ket. And then this gave us the wave function. Same thing here, except now there's n particles. And what you do is you expand both of these in terms of creation annihilation operators acting on the vacuum. So as promised, everything just reduces to creation annihilation operators acting on the vacuum, right? And then you use like Wick's theorem to contract everything. And in the end, you'll get the single particle wave functions, products of them, and they'll be all in the right, you know, they'll be properly symmetrized or anti-symmetrized, depending on if you have fermions or bosons. What else? Any questions about that? So to complete the picture, of course, this state itself, we could write either in terms of this basis, say energy level basis, or in terms of the position space basis. And so to complete the picture, I can write down an expression for this multi-particle state. Another way, I can write it in terms of the position basis as follows, if I wish. An arbitrary n particle state would be the following. I would sum over all of the different spin states, and I would integrate over all this is a product symbol now. It's a collection of n integrals over the n particle coordinates, right? I would have a bunch of creation operators generating particles in for spin states sigma and coordinates r. A bunch of these guys, and these are all going to act on the vacuum, popping particles in at those locations. And then for any particular coordinate configuration, there's going to be a coefficient associated with that, and that's just the multi-particle wave function, which is a number. So this sort of completes the picture. This is in the position space basis, or if I want to write it in terms of energy space basis, then I would use this. What I did, you just look back at the first lecture on second quantization. It's just that where you pop particles in at particular energies. So it's the same thing. That guy and that guy. Those things have to be equivalent. They're just different, either the position representation or the energy level one, and the sort of transformation between one and the other is just given by the wave function, the whole anti-symmetric or symmetric multi-particle wave function for the n identical particles. Okay. Any questions about that? Yeah, again, you'll get some practice of this kind of thing. But the key is there's a lot of complicated notation, but the key is again that these guys are nothing but a different basis for oh, sorry, these are the wave functions. Sorry. So big psi, these operators, which create a particle in spin sigma and location r, they're just equivalent to, but in a different basis of the creation and annihilation operators for creating a particle in a certain state, just a different basis. So yeah, and then what a multi-particle wave function is just any multi-particle state that you're interested in. It's the position space representation, so it's you know, it's where you specify the coordinates and spin states of all the n particles, because that's, you know, the wave function is a function of those things. That's what it is. That's what the multi-particle wave function is. And that's kind of it. And you know, these things you can write, and you can write both of these things as creation annihilation operators acting on a vacuum. So then you know how to calculate everything. And because of Wick's theorem, we know that any vacuum expectation value is going to be the sum of a bunch of the contractions, right? And it's that sum of the contractions that's the symmetrization or the anti-symmetrization. That's that Slater determinant, or you know, the symmetric Slater determinant. That's where it hides. It just hides in Wick's theorem in the second quantization formalism. But again, I'm just trying to give you this sort of conceptual tools here to understand this. Of course, if you really want to take advantage of this, you could take a kind of second semester solid state class. That's definitely taught here. You know, basically a second semester condensed matter course where you would do this kind of thing in detail. But it's, again, it's sort of outside the scope of what we're doing. I just want to give you a flavor of this stuff a little bit. So, all right, let's talk about now dynamics, because, well, now we have operators and yeah, these creation annihilation operators, and you want to deal with those because, again, we know how to calculate those with Wick's theorem. So what you want to do is, instead of using a Schrodinger equation for like the multi-particle states, it's hard. You want to deal with the Heisenberg picture and do the dynamics for the creation annihilation operators. So you'll practice that on the homework. But the basic idea is, what does your Hamiltonian look like typically for these things? Well, again, you have some single particle operator, include the kinetic energies and the single particle potentials. Then you might have some pair operator, you know, this guy, and you have a I dagger, a J dagger, and again, remember to flip the order of the annihilation operators. Like that. You have a Hamiltonian like this. And so what happens? Well, if we just look at the Heisenberg picture, and that means that our states don't evolve in time, but our operators do. And so our states, you could just always just consider the vacuum. In the Heisenberg picture, the operators will evolve in time according to the Heisenberg equation of motion, right? It looks like the Schrodinger equation, you know, IH bar, annihilation operator, change in time. It's just the commutation relation between your Hamiltonian and the operator. That's just the Heisenberg picture equation of motion. And you can show that, and this is shown in the homework, that you can do these commutation relations and find an equation of motion that looks like this. The commutator will kill one of the sums in both of the cases. Yeah. And I flipped K and L here. But it's the same. It's LK, but here I put KL. But anyway, you can derive this. You'll do that on the homework. So this is your equation of motion. And of course, again, there's nothing special about the basis that we use for the annihilation operator. So let me leave you with this thought here before you take off, is that you can just write this in position space too. You can say, well, in this case, the time evolution of, say, the position space annihilation operator, which is this big psi. And I put a time coordinate there to be explicit. It would be the one particle operator, and it might be diagonal. It's typically diagonal in position space. So you'll have some potential term, and you'll have maybe some gradients corresponding to kinetic energy acting on this annihilation operator. Or in this case, a field operator. And then you'll get another term, which again, if it's diagonal in position space, then it'll look like this. There'll be a pair interaction between between two places R and R prime, and you'll have side dagger sigma prime R T. Let me move this over. You'll have psi sigma prime R prime T. And this is nothing but the density operator for coordinates R prime. And then all of this is acting on psi sigma R R comma T. Let's see. Yeah, so what's the point of this is that this part looks just like Schrodinger's equation, except it's for these field operators. So it's really a Heisenberg equation of motion, but because these are not wave functions, they're operators. And it includes this extra term, which isn't present in any kind of Schrodinger equation. That's entirely due to the fact that you have multiple particles. That's the possibility for pairwise interactions, where you have interactions between pairs of particles. So we'll talk more about that next time, but I just wanted to just write this down for now, and then I'll say a little bit more about it. And then the last thing we'll talk about is how you can use this kind of stuff to understand electrons and photons, and a little bit, what you do if you want to include special relativity.